This video will cover Chapter 14, the Black-Scholes model. I'm going to cover an example that's on page 336, problem number 14. And here the stock price is $24.35. K is 25, R is 3%. It's already in continuously compounded form, so you don't have to take it to the log of anything. Just use it as is. The volatility of the underlying is 40%. Time is 12 days. Or 0.0476 years, and I'm going to value here the call and a put. And basically this video is all about just computing the price, get you familiar with what the model actually represents, and when you become familiar with what the model is, then we'll move into explaining it in a little more depth. But you kind of already have the intuition in the model. The intuition in the model comes from the binomial that we worked in the previous chapters. Take the binomial tree, dice it up the same time period, dice it up into infinitely many time periods, and you basically have the Black-Scholes model. Okay. Now the value of the call is going to be measured this way. Is going to be the call equals the stock price times ND of 1, and I'll explain what ND of 1 represents in a second, minus the present value of the strike times ND of 2. D of 1 is a standard normal variable. That term should be familiar from your basic statistics course. Let me show it to you for the Black-Scholes model. And I'll show it ever so slightly different form than the text. The textbook will show you it this way. Right, and then but I'm going to write it all under divided by sigma square root of t minus t. The textbook has this component written off to the side, but it doesn't matter. When it's in this form, it kind of looks like a standard normal variable. Remember standard normal variables from probability and stats? You had a z, it looked like this. You had a z variable, and z equaled x minus the mean of some random variable divided by its variance. X could be the height of people. It could be the expected life of a light bulb. And so what you're doing is you're looking at x relative to its mean and adjusting it by how volatile the x is. In other words, how spread out the distribution is. And so when you compute this standardized normal variable, you're capable of then using a standard normal table to compute probabilities, just like you did in statistics class. In the back of every statistics book has a table like this. Now I know you can't read this. The print is fine, but you have a z right here, z's coming down here in decimals, in tenths of a decimal, and then hundredths of decimal places, and this is the standard normal, but it's cumulative. It's cumulative probability, meaning if you compute a d that's greater than 1, in other words, or greater than 0, and it's positive, you're looking at all this area here. Now, if you compute a d here, it's just this area to the left of the distribution. It's cumulative. Okay? So then, what we need to do is compute this formula, and so this formula for the problem at hand is this. This term right here represents the percentage that the option is in or out of the money at this point. Okay? The percentage that it's in or out of the money. We're going to assume that little t is equal to, little t right here is equal to 0. We're going to assume that for nearly everything. Little t right here is equal to 0. And we take this and you crank through it, and you'll get minus 0.026 plus 0.005236 divided by 0.08727, and it equals minus 0.2419. And when you see minus here, it means we're to the left of the zero. We're somewhere in this over here. I'll draw you a new standard normal here. So here's 0. We're minus 0.2419. And so we're looking at the cumulative area here. Now, cumulative area is described, written down as this. Okay, so that's d of 1 right here. And it's negative. So you right away you know that this should be less. This area should be less than 50%. And it turns out that it equals 0.4044. 40% of this entire distribution, 40%, is to the left over here. Okay. Now that's one of the biggest hurdles. Now we need to calculate d of 2, and d of 2 is equal to d of 1 minus sigma square root of t minus t, and that equals minus 2419 and this equals minus 0.3219, and the cumulative normal density of this variable is equal to 0.371. 0.371. Now we can assemble the whole thing. We got most of the calculations done. So the value of the call is equal to 2435 times 0.4044 minus the present value of the strike This is the present value of the strike, and here's ND of 2. So we compute this to be 985 minus 926, which is about 59 cents. So the value of this option is about 59 cents, and ask yourself, does it make sense? You know, we're looking, go back to the original part of the problem. This option is slightly out of the money for a call option. It's 65 cents out of the money. And it does have a fair amount of volatility, but at the same time, it only has 12 days left. So given this high volatility, you'd think it'd be worth a lot, but given it only has 12 days left, it's not worth a whole lot. It's only worth about 59 cents. Okay. Now, how do you interpret this? This component right here, this basically says this is the present value of what you expect to receive. You know, so you have this call option. The call option is only worth money if the option finishes in the money. And you know, you don't know if it will or not. So there's a probability wrapped around that concern. And so this is what we expect to receive. And so this is the present value of the stock price now, and this is the ND of 1, which is also, remember, the delta C that we did in the binomial. It's the slope of the option price. And we tried to make the case, and we said you got to be very careful that this represents the probability of the option finishing in the money. It does somewhat resemble that. And so you can look at this as being, this is the expected value of what you expect to receive, and this is the present value, right? Here's the present value calculation of what you expect to pay out. And so you expect to pay out $9.26. And that's, again, adjusted for the probabilities of the option finishing in the money and taking into consideration time value of money. Okay, so what we're dealing with is expected discounted values. The term expected means it's adjusted for probabilities, and we're discounting back. We have to discount K back because K is a fixed number of 25. We don't have to do any discounting with the stock price because the stock price today is already a present value. So the option is worth the call option is worth 59 cents. Let's do the put. Now the put, once you have the calculations for the call, the put calculations are way easier. So it's the present value of K, right? ND of 2. So it's sorry about that. It's that term right, this formula right here. So the present value here is, let's see, this is $24.96. The present value of $25 discounted at 3% for 12 days. $24.96. ND of 2 with a minus sign in front of it is 0.629. Now let's look at something for a minute here. You have your standard normal, and if you have a D of 1, for example, here, right, and this is your cumulative normal density, and this is a negative sign in front of it, then if you take the same amount, move it over to here, and take the absolute value of it, and you get D of 1, then the cumulative normal density of this term, this whole term, plus this is going to add up to 1, because this amount is going to equal this area. So what I'm saying is that ND of 1 plus ND of minus 1 always is going to equal 1 in total. And the same thing with if you have ND of 2 and minus ND of 2. They're always going to add up to 1. So, and what this is saying is the normal distribution is symmetric. So keep that in mind. It will help you significantly. And you can see, for example, ND of 2 in the black calculation I just did was 0.37, and now I'm saying minus ND of 2 is 0.629. Well, that adds up to 1. And the same thing with D of 1 and negative D of 1. Well, it'll add up to 1. And this is 24.35, and this comes out to be, it's 1 minus, let's see, 0.4044, which happens to be .5956. Solve for the put, so sorry about that. 0.5956. So this is 1570 minus 1450. The put is worth $1.20. The option's slightly out of the money. Okay, so you would think that the put would be worth a little more than the call, and it is. So the next video we'll talk more about, how do you interpret this better. And like I said, it's hard. I said this in class. It's almost like a black box, not to make a pun out of the model. But if you have the the binomial option pricing model intuition, this is what's underneath. This